किधर गया यार?
स्टडी स्टडी फोल्डर।
हाँ, CMP किधर है? अच्छा, ये इधर खुला ना, नहीं दिख रहा होगा अभी। अभी दिख रहा है?
हाँ,
कूल। यार अनफॉर्चुनेटली लिखने के लिए नहीं मेरे पास कुछ।
इसमें व्हाइट बोर्ड होता है ना, आई थिंक स्क्रीन पे लिख सकता है तो।
स्क्रीन पे? हाँ, इसमें बोर्ड होता है, माउस से मैं थोड़ा लिख सकता हूँ, थोड़ा बहुत डायग्राम वायग्राम। स्टार्ट अ न्यू वाइट बोर्ड। अच्छा, एक कॉमन वाइट बोर्ड है, हम कोई भी लिख सकता है इसमें ना?
हम्म।
अब मुझे बताओ क्या दिख रहा है? सिर्फ स्क्रीन?
हबार्ड मॉडल।
सिर्फ हबर्ड मॉडल दिख रहा है ना?
पहली स्लाइड।
ओके, जो मुझे चेंज करना पड़ेगा जब मुझे लिखना है।
स्क्रीन शेयर करनी पड़ेगी जब तू लिखेगा, तुझे स्क्रीन शेयर करनी पड़ेगी।
ठीक है, कोई बात नहीं। इसी बट आई थिंक आई शुड स्टार्ट फ्रॉम राइटिंग समथिंग, प्रेजेंट समथिंग एल्स। हाँ, अभी क्या क्या दिख रहा है?
व्हाइट बोर्ड।
वो हबर्ड मॉडल नहीं दिख रहा, PDF?
नहीं नहीं।
ओके, तो एक बार में क्या दिखेगा? सो कोई बात नहीं, विल स्टार्ट
अरे
फ्रॉम
स्क्रीन, तुझे स्क्रीन स्प्लिट कर।
स्क्रीन स्प्लिट करो?
हम्म, म्हणजे व्हाइट बोर्ड आणि हे दोन्ही तुला ओपन करायचं.
अच्छा, एका स्क्रीनवरती का? कारण माझ्याकडे 2 मॉनिटर ना, मग दुसरं ते हे मी ओपन करून ठेवलं ऑलरेडी.
अच्छा.
आणि रेकॉर्डिंग जे होते OBSची आहे ना, ती एकाच मॉनिटरवरती होते. बट यू हॅव अ पॉईंट. हाँ, समझा मुझे. जब ये चाहिए होगा ये कर लूँगा मैं, जब ये चाहिए होगा
अरे
कर.
त्या स्क्वेअरवर क्लिक कर. तो जो
कुठलं?
तुला दिसतोय बघ स्क्वेअर,
हां,
मिनिमाइजच्या शेजारचा, मिनिमाइजच्या शेजारचा. क्लिक
मिनिमम.
नको करू. हा, आता
उसका।
आता येते. हा.
अच्छा,
हाँ
ये
राइट।
क्या?
यस यस।
आ! वो नाही, तूने चार चार वाला ओपन कर दिया.
हाँ। अरे तू शायद चार वाले भी किया।
हम्म.
हाँ अभी ठीक।
यहाँ पे क्या खोलो अभी?
ते वर.
हाँ, ठीक है.
प्रेझेंटेशन छोटं दिसतंय पण.
ते ह्याची व्हाईट बोर्डची साईज कमी कर ना, ह्याची ह्याची जास्त ठेव. जेव्हा लागेल तेव्हा त्याला मग तुला इन्क्रीज करता येईल. हा.
ते मॅक्स गेलं आहे, मॅक्स घ्यायचं.
जर व्हाईट बोर्डवर F11 दाब, व्हाईट बोर्डच्या स्क्रीनवर. नाही नाही, सॉरी, गलती हो गई.
तो इतना ही होगा शायद ये. ठीक है, मुझे ज़्यादा नहीं चाहिए राइटिंग स्पेस, बाद में PPT कर लूँगा. ओके, सो वी शुड स्टार्ट राइट. So what is Hubbard model? See, if you take a solid material and अगर आप ये लेते हो एस ऑर्बिटल वाले इलेक्ट्रॉन्स लेते हो, जाने दो ज़्यादा वो करने की जरूरत नहीं, मैं दिखाने वाला था पीरियोडिक टेबल, लेकिन जाने दो। इफ़ यू टेक द अल्कलाइन अर्थ मेटल्स एस ऑर्बिटल वाले, so their wave functions are very delocalized in the sense that the electrons are free in a metal, and सब हर आयंस से अटैच रहते हैं, so essentially वो फ्री रहते हैं ऑर्बिटल लास्ट इलेक्ट्रॉन्स इन द सोडियम एटम फॉर एग्जांपल, so their wave function is almost free. Okay, so e raised to I kx रहता है उनका वेव फंक्शन, प्लेन वेव्स। सो दे, और जब इसका आप मॉड स्क्वायर लोगे, व्हेन यू टेक द प्रोबेबिलिटी डेंसिटी, देन इट इज़ अ कांस्टेंट। ओके, सो मॉड साई स्क्वायर इज कांस्टेंट, एंड व्हेन यू कैलकुलेट j using this, then you get the current of these electrons and you get conductivity। आप उस पर ये लगा दो, इलेक्ट्रिक फील्ड लगाओ, एंड यू गेट द कंडक्टिविटी। नाउ इनके एग्जैक्टली ऑपोजिट होते हैं द इलेक्ट्रॉन्स विच आर वेरी लोकलाइज्ड इन द एटम्स, विच आर टाइटली बाउंड टू द न्यूक्लियस, and they have a very localized function. So if I wish to draw it, then these are plus ions, so their wave functions are very localized. In Ising model, which although was classical, but the electrons are very localized. One electron does not cannot go to other lattice sites. That is why the wave functions are very localized. So these two are very opposite cases if you want to consider localization as a parameter. इनके बीच में आते हैं d ऑर्बिटल, d ऑर्बिटल। So the wave functions स्कैंडियम, टाइटेनियम, इंडियम, क्रोमियम, मैग्नीज, फेरस, ये सब जो बीच वाले हैं, these lie in between these two extremes. Okay, so they have a wave function which will overlap. Admit. Okay, so shears is also there. I'll quickly revise. So in a metal, the wave function is e raised to I kx, hence the probability density is constant, and you get you have essentially non-localized electrons, and you apply electric field and you get a current. Opposite to this is the electrons which are very localized. So these are highly localized electrons attached to nucleus. They don't like to leave their own nucleus. In between these two are d orbital electrons, whose wave functions overlap. मतलब यहाँ का wave function है फर्स्ट आयन का और सेकंड का, इनके बीच में ओवरलैप रहेगा। सो इसकी वजह से क्या होता है, द इलेक्ट्रॉन ऑन दिस एटम कैन go to here, and you know it because it has spin, it will go here only if there is an opposite spin present here. So if opposite spin is present, then it can jump through, and these have various words. It can tunnel.
एक क्वेश्चन है,
हम्म,
ये जो प्रॉपर्टी है
हाँ,
लोकलाइज या फिर
हाँ,
नॉट लोकलाइज्ड,
हाँ,
ये स्फेरिकल हार्मोनिक से रिलेटेड है क्या, SPD? क्योंकि तुमने बोला कि एस में जो इलेक्ट्रॉन होता है वो लोकलाइज्ड है, डी ऑर्बिटल में जो इलेक्ट्रॉन है वो लोकलाइज नहीं है।
नहीं
नहीं, उसने बोला कि इस ऑर्बिटल में फ्री इलेक्ट्रॉन है, वो सबसे ज्यादा डीलोकलाइज्ड है इस ऑर्बिटल वाला।
एस ऑर्बिटल वाला
एस ऑर्बिटल वर्ड यूज़ करना करेक्ट नहीं है, क्योंकि जो 1s देखो, अगर आप hydrogen atom. It is very localized, right? And essentially the left side of the periodic table is a good example. The left side of periodic table है ना, alkaline earth metals और ये सब, and they
नहीं
show.
मतलब क्लासिफिकेशन कैसे करते हो कि एक इलेक्ट्रॉन लोकलाइज है या नहीं? जैसे मुझे लगा कि सॉलिड में जब तुम बोल रहे थे तो कंडक्शन बैंड में है, इसलिए वो कांस्टेंट सी ऑफ इलेक्ट्रॉन्स है तो उनके वेव फंक्शंस मतलब
हाँ,
ओवरलैप करते हैं
सो
पूरी
हाफ
तरीके से।
फील्ड जब रहता है, बैलेंस बैंड जब हाफ फील्ड रहता है, तो हम उसको बोलते हैं ना कि दिस इज अ कंडक्टर.
तो मतलब इनर मोस्ट इलेक्ट्रॉन होगा तो वो लोकलाइज्ड होगा, आउटर मोस्ट इलेक्ट्रॉन होगा उसके वेव फंक्शन जो होंगे वो
करेक्ट, वेरी
ये करेंगे।
ट्रू. लेकिन
करेक्ट।
आउटर मोस्ट तो डी ऑर्बिटल में भी होता है ना, जो बीच वाले मेटल, ट्रांजिशन मेटल्स रहते हैं, देयर
हाँ
आउटर मोस्ट इज डी,
करेक्ट।
राइट? एंड
हम्म।
दैट इज सेमी लोकलाइज्ड.
ओके ओके
Okay, so now uh, so there is a finite probability of electron 1 of atom 1 jumping to second, and second also can jump from here to here, and we want to like model this phenomena. We want to calculate ferromagnetism. The origin of Hubbard model in 1960s, 63, 62 was to explain this the ferromagnetism of these materials, in which there is not fully localization and not fully delocalization. Okay, so we want to model this.
रियल एग्जांपल क्या है इसका?
इसका रियल एग्जांपल NiO शायद उनको एक्सप्लेन करना था. आई डोंट रिमेम्बर एग्जैक्ट. शायद निकल ऑक्साइड उनको एक्सप्लेन करना था. द मॉट इंसुलेशन ऑफ निकल ऑक्साइड was not expected, शायद. हाँ, not sure.
अच्छा ओके।
So now, so topics what we will do today is, first I will introduce the model and what techniques do we use. Then after that we will develop some basic second quantization. सेकेंड क्वांटाइजेशन मैगी वर्जन 2 मिनट में सेकेंड क्वांटाइजेशन. फिर फर्मी एनर्जी आई डिडंट डू. फर्मी एनर्जी बहुत टाइम, बहुत कैलकुलेशन. बट आई विल इंट्रोड्यूस फर्मियोनिक बोसोनिक बेसिक डिफरेंसेस. ज़्यादा नहीं है, थोड़ा ही करेंगे, एब्जर्व होना जरूरी है. सो Hubbard model is a simplified quantum many-body model used to study strongly correlated electrons in condensed matter. Correlated, strongly, why strongly correlated, that also I will explain later कि कौन से systems होते हैं. And then it describes electrons in lattice, whether wave functions exhibit localization due to interaction with the lattice. Now the two important terms here are the kinetic energy and the potential energy, and this potential energy U is the count is the repulsion energy between two electrons in the lattice. See, ideally, theoretically, analytically, each electron will be repelled by other electron. This always happens. It happens even in metals, but because of the screening effect and everything, it appears to be free. But in this case, this U is very important. This is a real interaction which we consider U. You can put U0 and see what will happen. If you put U0, there is no repulsion between electrons, and they are essentially like the metallic electrons, like P.
Can you explain the notation? What is C dagger I sigma?
See, I just want you to look at this Hamiltonian, and we will go step by step. First we need to develop the second quantization, and then only we will understand what each letter, each index means here, because it is not mathematically, conceptually, it is not an easy thing to explain what is written here, I sigma cj. So ये सब चीज़ें हम एक्सप्लेन करेंगे, n क्या होता है, u क्या होता है, माइनस टी क्या होता है. ठीक है, सारा कैलकुलेशन नहीं दिखाऊंगा मैं, बट आई कैन गिव यू सम फ्लेवर कि इसका मीनिंग क्या है. So the techniques used to solve this model are Bethe and Sons. Bethe ये पता नहीं है, ये था कुछ तो Italian Hans Bethe था शायद, and he exactly solved the 1D version. So nobody has solved the 2D version analytically. So that is why I used numerical methods.
Vishwas, can you repeat what is the problem statement?
So the problem statement is to study the properties of electrons of these materials, the d orbital materials. So you need to calculate the ground state energy mathematically. You need to calculate ground state energy, what is the ground state of these materials without excitations. Normally वो if you give me इतना chunk of material तो उसका magnetism क्या होना चाहिए. That was how this model was introduced. Okay, so that is the statement here, and we'll use this to model the dynamics of this material. Okay, so next method is exact declination, which I have done, and this is a very exact method. See this if you can do a large number of calculations by hand, if you had thousands of hands and they can do, then this gives you exact results. Okay, analytically exact, no approximation, no perturbation, nothing. So in that sense it is very strong, and we use computer instead of those 1000 hands, but this is exact. Third method is quantum Monte Carlo. So classical Monte Carlo we know, and Devendra will be giving talk on classical Monte Carlo, and उसका ही quantum version है, and specifically it is which I have learned but not able to execute. It is called variational Monte Carlo. Okay, so you take a wave function, trial wave function, take a mod square. Okay, then you need to construct the probability density from Monte Carlo simulation, from the random walker. So you sample this probability density which came from quantum origin. You sample this from the classical Monte Carlo random walkers, and then you get.
Which distribution do you use?
Which distribution do I use? In bosonic it is a different distribution. I think in boson case it is simple Gaussian. If you trap Bose ions and you calculate the ground state, then they form a Gaussian. So that is the distribution, and you can calculate for any distribution where walkers you change. So since I have not perfected it and my ground state energy was not minimization, so variational में क्या करते हैं, there is alpha parameter, you change that parameter and you get the good ground state energy. So मैं हार्मोनिक ऑसिलेटर के लिए भी मैंने आया नहीं. So but this can be used for large number of sites. So the disadvantage of exact dilation that you can usually, it is exact but only for short sites. You require a large number of computational power to do it for say 100 cross 100 sites. So there is where quantum Monte Carlo comes into picture. And we have already done this exact dilation. Now we want to learn quantum Monte Carlo and apply it to this and see the properties. Fourth is renormalization, and unfortunately I don't know anything about renormalization. They also call it DMRG method, which I want to learn. Okay, so I don't have anything to offer in that case. Today I will tell you about exact dilation something. So what do we need for this? We need second quantization methods. So what is second quantization? What is first quantization? So first quantization is the idea that you take this classical variables, our x and classical variables, and elevate them to operators. So x p, x operator, p operator, and उनका combinations h operator, l square operator. You elevate the dynamical variables to operators, and the computation relation fundamental between the fundamental operators, that is x and its canonical conjugate p I h process. This is called as first quantization. Okay, so this is first quantization, and this will act on the state. Okay, so we can once you have done this operator thing, then you can represent them as a matrix, and this will act on the state which is represented by the wave functions to give you back an eigenvalue, say x operator. Okay, so this eigenvalue is the physical measurement which we do, and this operator acts on the state psi. So the state, so the operator here is, operators are the dynamical variables. Very hard to write with mouse. And this is the state. State is wave function psi. Very soon we will change this, so that is why I am writing it down. So now we have this is called first quantization, and you find the eigenvalue and eigenfunctions and everything you can do with this. Now what we will do is we will call the wave function psi, we will elevate the wave function psi itself to an operator. Okay, so this is a very strange thing we are doing here. How do we motivate this? There is one way to motivate it, is जब भी हम Lagrangian लिखते हैं, so when you write down Lagrangian say for a single particle, then Lagrangian for a single particle, Lagrangian for a Lagrangian for a single particle will spit out Newton's law, right? And you can also write Lagrangian for fields. So classical fields, you can write down Lagrangian for classical fields also, and that, yes, so if you write down Lagrangian for electromagnetic radiation, that will spit out Maxwell equations. Maxwell equations. Okay, so fields का idea तो इधर से आता है, classical fields जो हमारे थे, nothing quantum about them. So if we were quantizing the, in the first quantization we were quantizing the x's and p's, x and p's, the dynamical variables. So the idea here was that why don't we quantize the classical fields as well? And when you quantize the classical fields like electromagnetic fields, you get photons. So you quantize them and you get photons. Okay. Similarly, why don't you take wave function? This behaves something like fields, right? So why don't you pick up this wave function and write down a Lagrangian and quantize it? What you should get? You should get electrons. So you quantize them again and you get electrons. So this was the idea. Now Nipun knows better. I haven't studied this.
Yeah, I
mathematically.
think instead of calling this as wave function, you can call it as an electron field. Just like here you called it as a photon field or an electromagnetic field.
Mhm.
So when you quantize the electromagnetic field, you get photons. So when you quantize the electron field, you will get electrons.
Huh.
So the wave function is actually a field
Hmm.
which we can call it as an electron field.
Right. So every kind of particle in the universe will now have a field, and that is why, similar to how we are elevating these x's to operators, we will now elevate the wave function as operators. Hence, there is a cap on this wave function. So if it is a dynamical variable, okay, the psi, it will also have a canonical conjugate, which I will call it as psi dagger. So similar to how we had a relation between x and p's, these will also have a commutation relations between them. Now we can have two types of commutation relation between them, because there are two kinds of particles. When you are doing single particle, when you go from single particle to multi-particle in first quantization, you will need to include the idea of identical particles, and when you introduce that, then you will have to divide them into two classes, fermions and bosons, when you do many body theory. And here, if you want to do many body theory, there are uh, two different, what do you say, commutator, two different commutators. So in this ppt also you can see here. So the boson ones are commutator ones, or regular commutators with the delta function r1 r2, and fermions obey the anti-commutation, that is with a plus sign. Okay, so psi 1 r1, psi 1 r2, there is a plus sign in between, and you reverse that instead of a minus sign. This is what we call as anti-commutator. So Pauli exclusion principle is inbuilt in this, similar to how in identical particles, if you put the same state and you get a zero, so here also we get that. Next thing which you want is what is the, like, mathematically how do we write these operators. So these field operators can be written as, these field operators can be written as a product of creation operators. So if you put a dagger, this is called as, if you put a dagger on this, then this is called a creation operator. So C dagger is a creation operator. It creates particles in a particular state, and that state is this, our first quantization state, phi n. So these phi n's are the first quantization states. Like in hydrogen atom you have RYLM, in harmonic oscillator you have Hermite, and in free particles we have this plane waves. So these are regular first quantization. So if somebody tells you that is first quantization deleted, we don't use it, so it is very wrong. In second quantization we just use a better method, and like, at least relativistically there is also, you know, uh, relativistically the number
What
is
is
not
this
present.
index n?
This index n,
Quantum number?
this n
In
is not,
what?
I do, n is quantum number, but I don't know why it is written like this. This sir gave us as it is, and he was
No, I
uh,
think this is what
hmm,
happens in usual QFT also,
hmm,
except we deal with free fields. So there you take linear combination of plane waves. So here, since you are dealing with a bound state system,
hmm,
these phi n of r must be, I think, the one particle or Schrodinger solution to the Schrodinger equation
hmm.
for that potential.
Okay, okay.
So I think, for example, harmonic oscillator, if you take
Hmm,
this phi n will be those polynomials,
hmm.
Hermite polynomials
Right,
or
right.
something. Those solutions basically, psi n of r.
Now I don't really know why there is a summation. What is the, like, origin of the summation? I've used it, but I don't know the origin.
That I can explain probably, but we
Maybe
can
later. For now, we will take it as it is, and we will develop a operational knowledge of how to use this. So, and so we have defined our operators. Okay, now we have our operators. Whatever Hamiltonian we will write in terms of this creation and annihilation operators. Okay, and in a minute I will show you how do we write it. And so operators we have, but what will they act on? They will act on uh, a state which is represented by this. Now this state lies in Fock space. So a simple motivation of Fock space is given like, if you take first quantization, okay, then you have a multiple particles in multiple states. Okay, यहाँ पे एक हो गया, यहाँ पे एक हो गया. So one thing which we do is write the wave function for individual particles. So this is particle number 1, particle number 2. तो सबका wave function अलग है और सबका state भी अलग है. Okay, it is in state 1 particle number, particle 2 is in state 2. So when you have many particles, what you can do is go from Hilbert space to Fock space. In Fock space, you, instead of telling what is the wave function of each particles, you, importance is given to the state itself. How many particles are there in first state? How many particles are there in second state? Okay, and so on. So this will tell us how many particles are there in the first state. So there are 3 particles, so we will write this as 3 3 0 0. Okay, so you get the idea, right? Vacuum state is when you have no particles. Now if we want to generate particle, what will you do? If you want to generate a particle in vacuum, mathematically what we will do is we will act on this vacuum state. I will represent this vacuum state by 0, and with some factor, numerical factor, you will get back a state which has this index here, Ci. That index is for on which state is it acting, 1 2 3 4. So if I want to create a particle in the, let's say, second state, I will write C2 dagger acting on vacuum state will give us 0 1 0. So what has happened, we have created a particle in state 1 with a wave function of that state 1. Okay, sorry, 2 here, in this case 2, right? So we have created a particle, one particle in the state 2, and this numerical factor is same of that we used in first quantization. There we had ladder operators, right? So we pick up that analogy of ladder operators and their algebra, and we apply here same. Again, I don't know the exact reason. There is some very good explanation for this. So we pick up this, and this will have also commutation relation similar to what A and A daggers had in first quantization. So if you have generated here particles, now if there are bosons, we can obviously generate 0 1 2 3 4 10 particles, 100 particles in same state. And if there are fermions, we can only at max generate one particle in one state. If you include the spin, then in the same state there can be 2 particles. We'll discuss later, but this is the general idea. So important thing which we also do in first quantization is what happens if you act distortion particles. So we get nothing, 0. Annihilation operator on vacuum state should give you 0. Similar to how first quantization, the algebra is pretty similar. So we have operators and we have states. Now we will use this whole quantization thing in solids. in lattices. This is what is different from what we field theorists do, like for example in high energy. So see, earlier we were generating states, we were generating particles in any state, right? In any uh, in any basis state. Basis is a very good word. In any basis states. So if there is a free particle, we will generate the state, the our basis will be plane waves, right? If you are in a harmonic oscillator, time out. If you are in harmonic oscillator, they will generate the particles in our basis state will be that Hermite polynomials, and in hydrogen atom our basis state will be Laguerre polynomials and spherical harmonics. Okay, so that basis states are important. You need to, according to your problem, you choose the basis states. So in our problem we will choose the basis states as something called as Vernier functions. Okay, so Vernier functions are nothing but Fourier transform of Bloch states. What are Bloch states? Bloch states are solution to Schrodinger equation when you have a periodic potential. Bloch states when you have a periodic potential. Periodic potential. Okay, and these Vernier wave functions are exact basis state function we require for our d orbital electrons. So they look like this. They have a periodicity which is the same periodicity followed by potential. So V of R is V of R plus A. So these states also follow that same periodicity. This phi here is our Bloch states. Okay, phi is our Bloch states, and we take a Fourier transform of this Vernier wave functions, because we want to do a Fourier transform of the whole Hamiltonian. So our convenient basis states will be these Vernier wave functions.
This is discrete Fourier transform, right?
Right. This is a discrete Fourier transform. That is why there is a summation and there is no integration. On top of that, the important point is whenever we represent a state, like in first quantization, we use a index for that, right? So n is represented in harmonic oscillator, and n takes discrete values. K is the our quantum number for free particles. So k takes continuous values. Here, if you take a look at left hand side, this n is not the quantum number here. It will not represent our state. What will represent is this I, Ri. Ith position will be our, what we call, ith position, 1, 2, 3, I. This I will be our quantum state. Okay, so this is very different from what we do in first quantization, and it is also very different from what we do in normal QFT. So this I will represent our state. This comes from physical idea that a wave function, an electron in the ith position at some is will be orthogonal, will have orthogonal states to other lattice sites. So the physical, this is motivated by physical orthonormality. Normal orthonormality we have in our first quantization also we had there, even in QFT. This is motivated by physical orthonormality. So you can what?
Why is there index n on W? Because K and gamma are summed over.
Oh, sorry.
I index
I
is.
think this is a misprint. This is gamma.
But
Okay.
gamma is also summed over. Then why it is depending on gamma?
I will have to check. कुछ तो गलत लिखा है मैंने.
Vishwas,
Hmm. Yes.
uh, is the energy of every site is same?
Energy of every site. See, states don't have energy, right?
Sorry.
States don't have energy, right? We are
It,
representing states. Is energy of every.
no, but they are first quantization state, so they will have some energy, right? They will
Yeah.
satisfy the Schrodinger equation. H psi equal to E psi.
Ah, okay, okay.
States will have energy.
Right, right. Correct, correct. They will have energy, right, right. Sorry, sorry. So they
So
have
I
the
think that
atomic energy, right?
small n on the left side of the formula is representing the energy at the ith site of. But if all of them have the same energy, then we don't need small n. But I don't know whether all of the site has same energy or not.
If there is a free index on the left hand side, which is
Mm-hmm.
n, then there should also be a free index on the right hand side, which should characterize this n. Means what is happening if I change this n on the left hand side? There is no effect on the right hand side. It looks like all n are same.
What
So
what I remember is that the band index should be there on the left hand side. Okay.
What is
then
band
it's
index?
gamma, W gamma.
W gamma band index should be there.
But then my question is, why are
You
you
can't
summing
sum
over
over
gamma?
gamma.
Hmm. I don't think.
I don't think then the sum will be there over gamma, because if the W depends on gamma, it
Hmm.
will be for a specific gamma.
Right, right. I
So
understand
the
your question.
sum will only be over K, I think.
Let's check on Google. Linear diffraction.
Psi n is there. Wn is there. WNR, but these are without the banding tricks. Oh, so sometimes see, it is problem of notation. Sometimes they use gamma and sometimes they use n. So the n here is gamma itself. Gamma is the band index. Summation is not over gamma.
Hmm.
Summation is over only k,
Okay, then it
right?
clears the doubt.
Hmm.
Yes.
Okay. So this is a typo here. Sum is not over gamma, and we do Fourier transform for that. E raised to I, only k रहना चाहिए. So we have our basis ready. Now you want to represent like 10 particles are here, 20 particles are on the other side, 30 are on the other side. Then you can simply write down n1, n2, ni. So for n lattice sites, this is the state how we represent. And I here is the site itself. And I think I had written orthonormality between this. So you can write orthonormality between these states, Wn. See, if you had done this linear combination of atomic orbitals and you found these uh, molecular states using perturbation, the interaction between them is, if it is perturbation, then you form a linear combination of atomic orbitals. There is a physical orthonormality. If you take multiple atoms and try to make solid out of them, there is also physical orthonormality involved. So it is motivated from that.
So this tells you that a state at the ith site is orthogonal to the same state at the jth site,
Right,
where
right,
I
right.
is not equal to
See,
j.
delta has Ri, capital Ri, and capital Rj. Capital Ri represents the position of ions and
So
not the
in the
electrons.
equation, I think there should be Rj somewhere on the left hand side,
On the
either one of the two.
Oh, you're right. This here also there is typing mistake. So the right hand side will be J. Okay, so we have this orthonormality, and now
Vishwas, I have one doubt.
yes, yes.
Suppose we compare, suppose let's say we are considering harmonic oscillator energy spectrum,
Hmm.
right?
Hmm.
Suppose all are in ground state. So let's say I provide some energy, some of them will go in first excited state, then
Hmm.
I will provide more energy, they will go in second excited, like that. So
Hmm.
when I'm providing energy, they are going to higher and higher level. So
Hmm.
now, so by providing energy, the hopping or the shifting is happening. So how here the shifting will happen from one side to other side? By giving more energy, is that true?
Hopping will happen by giving more energy. Right, it's a good question. Do we already fix energy? There is a hopping parameter T, which uh, which is equivalent of p square upon 2m, the kinetic energy term. Okay, so if you have enough kinetic energy, then it will jump from
Yeah.
a
So
state
so
to
the,
second state.
now my the second question is, so it means that the fourth side has more energy than the second side, right? The fourth is the higher higher excited side than the second. Is it true?
See, if it has spin, let's say it has up spin here and it has down spin here, so going from here to here
Mhm.
first will cost energy, but when it has reached here, it knows that the energy will be lowered, because this
No,
is
consider we will
hmm,
take simple. Consider we are talking about the bosons, so
hmm,
the spins will not matter, right?
right. So we have one boson, here second boson, but these
Okay, so
bosons have a you know these bosons have this interaction energy of u.
hmm,
Okay, so if the repulsion is more, then why will it jump? It won't jump if u is high.
No, I think what we are missing is that these electrons or bosons also have kinetic energy. So there is a competition between kinetic energy and
And
potential
potential
energy.
energy, right.
So you
okay,
don't have to provide energy from outside. I think these inherently have some kinetic energy, and based on whether the potential energy is repulsive or attractive,
Hmm.
these will move in the solid.
Right.
Means that is what I have understood. I don't know if it's right
Yeah,
or
it's right, right, it's right, it's perfectly all right. But it is a good question, right? If you take that same analogy.
is that what your question was?
yeah. So my question is that all these hills is of the same height. If they are of the same height, then why then can they have the same energy levels or they are the different energy levels? I'm not understanding.
If they have the same height, if the hills have the same height, hills are wave function, right? You mean potential,
Oh,
right?
yeah. You're showing hills as a potential, right? Not as a wave function.
No, potential is something like this, right?
Yeah.
Potential is something like this.
Hmm. If the all potentials are equal.
Ah, because the potential is periodic, so you are asking either they have same energy or
Yeah, so
no.
my question is, let's say there is a electron in 2,
Hmm.
so it will not leave 2 uh, if we neglect the quantum tunneling, right?
Hmm. Yes, it
So
won't live to.
so if I want to hop it from 2 to 3,
Hmm.
so do I need to give it more energy, or I don't know how to go
No,
from 2 to 3?
I think the potential energy term that he's going to write in the Hamiltonian, that will exactly simulate these movements, because then the electron at ith site will
Hmm.
interact with electron at jth site.
Okay.
Without that interact, just like we do in QFT, if you have just free theory,
Hmm.
then particle at some space-time point will not interact with other particle unless and until you put some
You
interaction
specify
like
the interaction. Okay.
phi cube or phi raised to 4, something like
So
that.
what we do
Here,
is we write
at this
H.
point, I think this is
Hmm.
free theory. And now, when he'll switch on the interaction, which is his
Interaction, right.
potential energy, then this hopping and all these things will happen probably.
Hmm.
Hmm. So we take this H, and we had written in the this something. So H is minus T plus. So this is the kinetic energy term, and this is the potential energy term. So U is the potential energy between two electrons. So divide this h either by t or by u, and you will get one parameter u by t. So the ratio of u by t will decide how much hopping will happen, how much will don't happen. And
But now if you put u equal to 0 in this equation, nothing will happen. This is just a static model.
no,
Electron cannot
if you
jump
put
from
u0, then it is a free model. Then conduction is
free
possible.
model.
Then conduction is possible. And if you put very high, and that is exact theorem of Nagaoka's theorem, that if you put u as very high compared to t, then what happens is that electrons try to be as far as possible from each other, and in doing so they have equal spins, all they have spins ups, and the material shows ferromagnetism for high u.
Yeah, so I'm confused about this. So these U are defining the heights of the potential. Sorry,
No,
the well of
u
the potential
u is the
or interaction.
potential energy between these two electrons.
So U is
Hmm.
defined as interaction.
U has nothing to do with this plus ions and these electrons.
No, no. My question is, what is showing you as the well potential well?
Potential well is made by these plus ions, right?
This plus signs. Okay. So my question is, when U will be zero, then electrons will be trapped
When
if
u
there
will
is no
be
interaction.
0, no. See, don't consider the interaction between this electron and this
And
plus.
the second electron. Oh.
Okay,
Acha. So this is the assumption that
right. So this
okay,
is the
that
assumption.
electrons are free.
So these
Okay,
are
okay,
outermost
okay.
cells. The
Now I
potential is
understand.
made by core. So u is between this and this electrons.
अरे ते नॉर्मल आपल्या फ्री
हो
ह्याच्यात
हो.
क्यूएफटी मध्ये पण असंच होतं ना.
Okay.
तसंच आहे आय थिंक. फ्री थिअरी मध्ये ते इंटरॅक्ट नाही करणार
Okay.
इलेक्ट्रॉन्स दोन
Hmm.
नेबरिंग साइड्स मधले.
Yeah.
So that is the outermost, and we are only want to simulate the outermost electrons. So we don't care about the core electrons. Okay. So in fermions, when they have spins, you can represent up spin, down spin, two spins, right? And for two electrons, you can have all the possible states. So this is what we do in exact animation. Given number of sites and number of electrons, you generate all possible states, and you can follow develop an algorithm how to do that. And here, for example, we have four. So this you do by hand, and again there is a typo, but this is the same Hamiltonian as previous. So you generate the states, you act each state on use this operator act h on these states. Okay. And in general what will happen if you have say four states, okay, and I represent them by 1 2 3 4. Let's do. So these states are numbered by 1 2 3 4. Okay, we act h on them. In general what will happen is they will form they will go into some linear combination of these basis states. They will stay within this basis states. So let's say acting h on 1 will give me it might return 1 also, or not 1, say 2 plus some number times 4 and not 3. So acting h on 1 will give me 2 plus 4, linear combination 2 or 4. Then you act the bra on this, right? So you will get a non-zero value when you act 2 here and 4 here. So those elements will be non-zero. So one by one you generate this whole matrix, H matrix. Then you diagonalize it, and you can find the ground state energy, and which is the ground state eigenvalue. So for large u, and for large u you can uh, for large u you will get a ferromagnetic. So this state will be the ground state. This state or this state will be the ground state. Similarly, you can do for bosons. Now, for bosons, because the number of particles can be on
If
each side.
u is 0, then this matrix is diagonal, right?
If u is 0, no. If t is 0, then matrix is diagonal.
If t is 0.
right? See, because number operator will commute with this, right? H. So for example, if you take this first state, okay, we'll take this first state and apply u on this. So u operator, only this part, second part, acting on this first state, will tell us.
Okay. That is clear, I think. So this potential energy is only between uh, two electrons at the same site.
Right, because there is up and down, right? We have cut down. I did forgot to mention. We have cut down the electron. In general, every electron will be correlated. Will be repelled by every other electron, right? But
Mhm.
uh, what Hubbard did is he took the strongest interaction, which is the on-site interaction.
And
And
in the first term, kinetic term,
hmm,
this sum over sigma, what is this sigma?
sigma is the spin index.
So plus or minus for an electron,
Yes, up down,
up or down.
up or down. So why?
And 1 and 2,
And
C dagger 1,
see,
2.
first site and second site.
So, okay.
I have not written it
Okay.
clearly. I should also have expanded this spin.
Can you apply H on any one site and explain
Ah,
how it's working?
beta. I have already done this, so I will just present, share with you. So is this visible? Wait. अरे इसमें नहीं है. एक मिनट.
अजून किती टाइम लागेल तुला विश्वास?
लास्ट हाथ से. I am almost done.
ठीक आहे, ठीक आहे.
हाँ. डाउनलोड करके रखना चाहिए यार. दिख रहा है क्या ये? हेलो.
हां.
So if I act H on first state, right? So there is the first term. What will the first term do? It will jump from annihilate the particle up spin from the second site, and it will create a second particle on this site first site. So we will get this term, okay, which is the second state itself, which is the third state itself, okay. Then another term. So you can have both possibilities. Either the upspin will travel here or the downspin will travel here. And because there is no particle here on the zero side, that term will be zero. So we don't have that states. Plus there will be potential energy u, because so we will get u times return back the same states. Similarly, you can do this for plus sides. Here the electron can jump and go into this state, or it can jump and go into this previous states which we have already done. So if you act on one particle on one state, you will get back other states, linear combination of other states, and then you can generate this matrix. So for two electrons, you get this 6 cross 6 matrix. You diagonalize it and you get the ground state energy.
So I think kinetic term is telling that the electron will hop only if the spin on the neighboring site is opposite or the site is empty,
Right. So when you expand that spin index, you need to
and that's why
actually.
it's non diagonal.
That's why it is non-diagonal because of the kinetic energy term.
So this is actually different from how it happens in normal QFT.
Okay.
Actually, in normal QFT, the kinetic term is always diagonal,
Acha. Okay.
and interaction is always non-diagonal. And
Okay.
this actually happens in normal quantum mechanics.
Oh. Okay. So I think we can end here, right? So there is boson version of this. We can do this for bosons. Right? As we know, in conductors, superconductors, bosons travel in the metal, right? So two fermions, they couple with each other, form a Cooper pair, and they travel as bosons. So you can model this Hamilton, the dynamics of this using bosonic Hubbard model. So if you are able to solve 2D Bose-Hubbard model, then you can understand the dynamics better. So I am currently doing that. So I think I will stop here. If you have any questions, you can ask.